Hello, everyone. My name is Shervin Bagheri. I'm a professor at KTH, and I'm going to present to you today a work that's been mainly done by Aidan Reinhardt, a PhD student in my group, and Ujis Lassis, a senior researcher, in collaboration with Thomas Salès from Bordeaux. So the title is A Lift Force Between Objects Due to Wall Slip Variations. And so basically, what we are looking into is particle-wall interaction. So the particle could represent the cell, fiber, or bubble, and the wall could be some complex wall, soft, porous, or inhomogeneous. And we want to understand the forces that are acting on this particle as this particle travels very close to the wall. In particular, we're interested in lubrication forces on the particle when the surfaces of the cylinder or the wall are non-trivial. So the simplest case, a canonical case, is a rigid cylinder that is moving parallel to a rigid wall. This is the simplest possible configuration we can think of. Now, even if the cylinder is free to rotate or translate in any direction, what will happen is that there will be no wall normal displacement. So the cylinder will keep moving parallel to the wall if the gap between the cylinder and the wall is much smaller than the radius of the cylinder, as well as if the Reynolds number is very small. So there is no displacement away from the wall. And that is a bit counterintuitive because you would think that the presence of the wall would sort of break the symmetry of the problem, and thus there should be some sort of a repulsion force on the cylinder. But that's not the case for very low Reynolds numbers. And this was explained already by Reynolds in 1886. And basically what Reynolds did here is a sketch from his paper where the bottom is a cylinder which is moving to the left at a constant velocity, and at the top we have fixed flat plate. Now, what Reynolds showed analytically is that to enforce mass conservation in the thin gap between these two objects, there is a pressure gradient that is induced. And the pressure distribution in the gap has this antisymmetric form. So when you integrate this pressure, the normal force induced by the pressure will be zero. So this is the explanation of why the cylinder and the wall there's no repulsive force between them. So what happens now if you look at more complex situations? This is what we are more interested in. So the question we ask is, what happens if the wall of either the plate what happens if the surface of either the wall or the cylinder is inhomogeneous? So that could refer to a variation of surface charges, wall roughness, wettability, or temperature that is changing. So clearly what we can expect is that this sort of antisymmetric form of the pressure in the gap will be disrupted, and there will be a net force in the wall normal direction. So the cylinder, if it's free to move, will probably be somehow pushed away from the wall, potentially. However, we don't really know how this works, and this is what we want to investigate. So what we did is that we modeled wall inhomogeneities with a boundary condition. So to model a change of properties on the wall, we varied the slip. So here in the blue here we have slip, which is modeled by a Navier slip boundary condition, and to the right we have no slip. So we can sort of modify the properties of the wall by changing the slip length in the Navier slip boundary condition. So what we tried, for example, is that we solved Stokes equations with this sort of boundary conditions that is alternating between slip and no slip, as you can see here in blue. And what you can see, if there's a cylinder that is falling parallel to the wall due to gravity, that it will actually show an oscillatory behavior. So when it goes from slippage to no slip, that is from a blue to a gray zone, then there will be a push force. The cylinder will be pushed away from the wall. And then when it transverses a gray zone to a blue zone, such that it goes from no slip to slip, it is pulled towards the wall. So as the cylinder is moving parallel to the wall, due to the change of boundary conditions, it will sort of go back and forth like this. And it turns out that if you simulate this for a very long time, there is actually net migration away from the wall. That is because the push force is slightly larger than the pull force. So we have tried many different type of configurations, and there's a range of non-trivial behaviors that emerge when you change the boundary condition on the wall. So how can we explain this? One way of doing this is to look at the lubrication approximation. So we do a standard lubrication scaling, as is shown here. I will not go into details, but two important parameters here is the contact length, LC, which is shown to the right top, and the ratio between the gap thickness to the radius of the cylinder. So if we non-dimensionalize it according to standard lubrication theory, we obtain the reduced equations from Stokes. These are basically Reynolds equations, or the same equations that Reynolds derived in 1886. Now, what we changed only is really the boundary condition at the bottom wall, such that its slip length here is big L in non-dimensional form, and there's also a step function S here, which is 1 if x is smaller than 0, and 0 if x is larger than 0. So this is basically the only modification we did to Reynolds equations, and we can solve these analytically. And when we do that, we can form the resistance matrix, basically describing the relationship between velocity on the cylinder and forces on the cylinder. So as you can see here, in 2D, we will have two components of velocity and angular velocity that can be translated to forces and torque on the cylinder through the resistance matrix R. So the components of R are basically resistance coefficients, or friction coefficients, if you like. So how, if we take a look at one particular mode, for example, a cylinder having imposed constant velocity, which is parallel to the wall, then the coefficients of the resistance matrix which are relevant are the first column. So we can see what forces that are induced on the cylinder from this particular motion by looking at these coefficients. So we can obtain these coefficients analytically from our analytical solution of the lubrication equations, and we can plot them as a function of the slip length. So we see that when the slip length goes to 0, there's only one non-zero resistance coefficient, and that is the drag term. So basically, for 0 slip length, or 0 transition, let's say, from slip to no slip, basically just a perfectly homogeneous wall, we obtain only the drag, which is basically also what Reynolds obtained. Now, however, if you have a transition and the slip length of this transition increases, you see gradually that you have a lift coefficient that emerges and also a torque that emerges. So this is basically showing how the lift depends on the slip length, and it clearly saturates for large slip lengths. So we can also perform a simple scaling analysis of this. So if we do that, we see that the lift force is proportional to the viscosity eta, the velocity of the cylinder, which is parallel to the wall, v, the radius and the slip length, L, as well as the inversely proportional to the gap thickness to the power of 2. Now, we can compare this to soft lubrication, or the elastohydrodynamic force, which has been investigated a lot. And here the lift force for a cylinder is shown to the right, and there we see a little bit of different scaling with respect to both viscosity and velocity, as well as the other parameters. And it also involves big H, which is the height of the soft wall, as well as Young modulus. So the question we wanted to ask is, how does this force induced by surface inhomogeneities compare to the elastohydrodynamic force? So what we did is that we compared to a very recent work where they directly measured the EHD force at a nanoscale using an AFM setup. So basically they have a substrate which they oscillate in parallel direction in the X direction here, and then they measure the normal force on a sphere that is attached to a cantilever. And when they measure the force, they basically see that the force is of order of nanometers. For example, for displacement, or for a gap thickness of 50 nanometers between the sphere and the substrate, the normal force is 10 nanonewtons. So what we wanted to see is if we use our scaling estimates for what parameters, or for the same parameters as this experiment, how much of a surface inhomogeneity quantified by a slip length would induce the same normal force. So we can extend our scaling to, or adapt it for sphere. Remember that we developed the scaling for cylinder, but that can sort of be approximated for sphere by multiplying it by contact length, LC, which results in this following scaling. And now if we insert the parameters from this experiment, we see that we can actually get a normal force from surface inhomogeneities, that is 10 nanonewtons for a gap thickness of 50 nanometers, if we have surface property variations quantified by the slip length of the order of 1 nanometers. So that is very, very small surface inhomogeneities can produce normal forces that can compete with the elastohydrodynamic force. So to conclude, any quite small surface inhomogeneities can induce lift force that are comparable to other lubrication forces, we believe, for example, the EHD force. This has consequences, for example, for experimental accuracy, where obviously there are defects in fabricating surfaces as well as measuring, and also for applications, for example, red blood cells, they could definitely have lift forces induced by surface inhomogeneities. Clearly, biological interfaces in particular are highly inhomogeneous. So from the reciprocal theorem, we can also basically perform the analysis for Janus particle over smooth wall. It turns out that it's the same results holds for just the reverse problems. We have a smooth wall, but the surface on the cylinder is inhomogeneous. I didn't talk anything about this. If you want to know more about that, you can look at our recent publications in PRF. So clearly, we are interested in extending the theory a bit more rigorously for spheres, and also interested in performing AFM measurements to really observe this normal force experimentally. And we will be very happy to, if somebody is willing to help us on AFM measurements, or if you have any questions, of course, on this presentation, don't hesitate to contact us, and you can find all our contact info at this website.